This week we will be synthesizing a dye, and not just any old dye, folks. This week we're going to be synthesizing a pH indicator, so that should be kind of fun. So here's the reaction this week. I think certainly if you've read the protocol or if you look at this reaction, it seems a lot more complicated. And in terms of the reaction itself, there are more steps than there have been in the past couple of weeks, but that's all right. We can get through it together. For this reaction, I want to show just part of the mechanism, and this will probably be the part of the mechanism that relates most to what you're learning in class. I want to start by drawing the nucleophile in this reaction. So you're probably learning about EAS and NAS mechanisms in class, and hopefully you recognize that the substituent on this benzene ring is an electron donating group, so it can push electrons into the ring. Now, when I say that, you probably also think, oh, that means, it directs ortho or para. Why is that? So, if we resonate that lone pair for the nitrogen into the ring, then we can draw a couple different resonance structures. And Dr. Livesey accidentally drew one too many double bonds there. Fix that real quick. Okay. So these electron donating groups create these beautiful kind of carbanions on the benzene ring. We can draw another resonance structure. And I'll make sure not to accidentally draw too many double bonds this time. And so this can show us why electron donating groups direct either ortho or para, because the lone pairs will end up either on the ortho position or the para position. So this can kind of show us that the nucleophilic attack is going to happen from either of these positions. Now, if we think in terms of like steric hindrance, right, the para position is more open and available because it's not next to this, bulky group. So, as long as, the para position is open, it's going to be preferred. So let's talk about the mechanism now. Okay, let's start by drawing our two reactants. Reactant number 1. Reactant number 2. And we can start this mechanism off by having those electrons on the rightmost reactant push in to the benzene ring. couple of different arrow pushings there, folks. Oops. Did not mean to draw a resonance arrow there. So what you can see is that our nucleophile here attacks this nitrogen, and we can resonate this triple bond on over. Let's see what we've made. Okay. So what next, folks? We can recognize that we can also draw a resonance structure of this kind of reactive intermediate as well. And when we draw this resonance structure, you can see that we're left with a carbocation rather than the positive charge being on the nitrogen. So this makes it a little bit more obvious, folks, that we're not yet done with this reaction mechanism. There's one more step here for us to complete. And so this is the point in the reaction mechanism, or in the protocol, and if I check it real quick, where we add sodium hydroxide. This is at step 4, it looks like. We add some sodium hydroxide. We need a base catalyst to finish up the rest of this mechanism. So let's add in our beautiful base. Now, to finish up this mechanism, folks, we need to realize that basically we need to deprotonate at the position where we had the nucleophilic attack. Now, sure, this proton isn't super acidic, right? But completing the reaction mechanism and kind of continuing this beautiful conjugated system that we have by losing that proton is super favorable, right? So that is why this type of mechanism is possible, because it results in a product that's super favorable. And so, folks, at the very end, we have our beautiful methyl orange product. just like that. So you can see, folks, that now the conjugation extends throughout the entire molecule. This is actually the most conjugated product we've made so far in this lab. You might recall that just last week with the aldol reaction, we made a slightly yellow-colored molecule due to the extended conjugation across that molecule. This is even bigger, even more conjugated. So keep an eye out on what happens in the various steps in this reaction and look for color changes. So that was a pretty intense mechanism, folks. The mechanism or the reaction itself can be called an azocoupling. In order to do this type of azocoupling, we need something called the diazonium ion. So the diazonium ion was the one with the triply bonded nitrogen. But then we also need a nice electron donating group to attack that electrophile. We got to make that benzene ring more nucleophilic with that dimethyl functional group. We just talked about how the nucleophile is activated at ortho and para, so that should make a lot of sense at this point. Let's talk about a couple different steps in the protocol that will be important this week. You'll notice that in almost all of the steps of this reaction, it mentions stirring. Some of us found out earlier in this semester that we have to choose an appropriately sized stir bar. If you choose a stir bar too small, the reaction won't mix thoroughly. And actually, if you choose a stir bar that's too large for your vessel, it also won't stir very effectively. So let's make sure we pick an appropriately sized stir bar. If you're not sure, come check with me. My other comment, folks, is that a lot of people tend to really turn up their stir plate to really fast speeds. Sometimes what happens if you turn it up too high is you'll notice the stir bar actually stops stirring. So don't stir too fast. Slower is actually sometimes better for thorough mixing. A note that I want to make this week is you want to think about the solubility of our reactants. You'll see that to the sulfonylate acid we add sodium carbonate, and you'll see that to the dimethylaniline we add acetic acid. So to one we add a base, to one we add an acid. Think to yourself about why this is necessary. You can probably expect to see this on a quiz. Why do we have to add acids and bases? It has something to do with the solubility of the reactants in aqueous solution. We also add a base catalyst near the end, that aqueous sodium hydroxide. And then when we wash upon vacuum filtration, you'll notice that we add some spectator ions in, some sodium chloride. Why might that be? To wrap up this week, folks, let's talk a little bit about methyl orange itself, our product, our beautiful product. It is an acid-base indicator. Maybe you've used it already in your general chemistry labs as a pH indicator. How exactly do indicators work? They change color when their protonation changes, right? The acid form, the conjugate base form will have a different color. So generally, folks, large conjugated systems, very extended conjugated systems, tend to have color. Electronically, they're just right to absorb some wavelengths of light so that we see color. What happens, though, when we have protonation, either at the acidic functional group, such as over here, or if we have protonation at the more basic functional group, which happens over here, the electronics of the conjugated system changes. The wavelength of light, then, that this molecule will absorb changes because of this, because the electrons are at a different energy state. They can be excited differently. So we should see different colors upon various different steps of protonation. So keep a very close eye on the color of your solution as you perform your titration once we have made product. As a quick note, I do just want to remind us of some general pKa's. This kind of sulfuric acid-like functional group generally has a pKa near 3. And the amine-like functional group generally has a pKa around 9. If you need a refresher on pKa, I do highly recommend that for this week. Now, just last thing, folks, I want to talk a little bit about dyes, because dyes are actually kind of like the founding element of organic chemistry today. So until the 1850s, to get dye for your clothing, you had to, go to the fields, harvest some flowers, and extract the color from that source. However, by accident, almost in labs, dyes were created, and this kind of spawned organic chemistry. So now, rather than, harvesting color from plants and animals, we just synthesize it in a lab. And that's why colorful clothing is kind of commonplace today. Whereas back in the 1850s or earlier, very colorful clothing was a sign of wealth, because you could pay for people to go harvest millions of flowers, right? So dyes, they're important for you and I, so we can look good. Last thing, folks, this week's green chemistry. We have use of renewable materials. So, when we're doing our chemistry, we don't want to be using very rare elements found on the planet, right? We don't want to cause a scarcity of any particular compound, element, molecule. So let's use something renewable so that we're doing less harm. Additionally, and this is, not so important in our lab, but is incredibly important for synthetic organic chemists who kind of do this for a living, reduce derivatives. If you can simplify your method, simplify your protocol with kind of fewer intermediate steps, usually this means there's less waste. You see here, I say fewer protections. Sometimes to do good organic chemistry, you have to put a different molecule on to protect a functional group. And then later you get rid of the protective group to continue your chemistry. That in itself is technically a wasteful step, because the molecule that was used to protect kind of wasn't really a part of the product. That wraps up things for this week's recitation, folks. Here is your cat meme having to do with dyes. See you in lab.